Hey everyone, and welcome to this explainer. Today, we're stepping right into the Master Craftsman's workshop. I really like to think of C programming as more than just typing out code. It's a physical craft where you are directly handling raw materials. Unlike other programming languages that kind of hold your hand and manage all the cleanup for you, C hands you the heavy machinery and just expects you to know exactly what you're doing. If you want to build truly high-performance software, mastering this machinery is absolutely crucial. So let's just dive right in. We've put together a definitive toolkit for conquering the most notoriously intimidating parts of C. Look, memory management can feel completely terrifying because one wrong move can, crash your entire system. But honestly, it doesn't have to be that way. Today, we're going to walk through a foolproof guide to 5 essential tools: man, exit, calloc, realloc, and Valgrind. By the end of this explainer, you won't just understand them, you're going to wield them like an absolute pro. Well, finding answers in C is actually incredibly simple. Meet the man command. Man is just short for manual, and it's a built-in help system right there on Linux. You don't even need to go searching the web. The entire spec sheet is already sitting in your terminal. Just type man followed by whatever function name you're curious about. For example, if you type man exit, you get everything you could possibly need to know about the exit function. It gives you the exact description, the syntax, the parameters you need, the return values to expect, and even code examples. It is literally your ultimate reference guide. Moving right along to Section 2, Essential Memory Functions, the core toolkit. We're stepping up to the workbench now. Let's look at the primary tools you'll use for managing raw memory. We have exit 3 for ending your program, calloc for allocating perfectly clean memory, and realloc for when you need to change the size of that memory later on. These 3 functions basically dictate how your program lives, breathes, and eventually dies. Let's start with exit. Think of this as your machine's master kill switch. When you flip it, the program stops immediately, no questions asked. But flipping the switch isn't just about stopping. It's actually about communicating exactly how it stopped. For instance, exit of 0 tells the operating system, hey, success, everything worked perfectly. But if memory allocation fails, say your pointer comes back as null, you'd use exit of 1. That signals a general error. It is a really crucial habit to let your system know whether things went right or wrong. Next up, we have calloc. Imagine you're renting a storage unit. You wouldn't want a unit filled with the last renter's leftover junk, right? You want it totally empty and swept clean. Well, that's exactly what calloc does for your memory. It allocates the space, but then it automatically goes in and fills it all with zeros. So if you allocate space for integers, they all start as zeros. If you allocate space for characters, it's a completely blank slate ready for a string. It's a guarantee that you are starting your work in a perfectly clean workspace. Now, you might be wondering, how does this actually compare to its famous sibling, malloc? Let's strip this down to the bare bones. Malloc gives you memory super fast, but it just leaves whatever random garbage was already sitting in that memory from before. Calloc takes a tiny bit more time because it actively cleans the memory, filling the whole block with nice, clean zeros. There's also an exact syntactical difference in your code you'll want to remember. Malloc only takes one single parameter, the total number of bytes you want. So malloc of 40 just hands you 40 bytes of garbage. Calloc, on the other hand, takes 2 parameters, the number of items and the size of each item. So calling calloc of 10 size of int gives you 10 integer spaces, perfectly zeroed out. Both lines give you 40 total bytes of memory in the end, but calloc, that gives you peace of mind. All right, on to Section 3, Safe Memory Resizing, expanding the unit. So what happens when your project grows and that storage unit you rented is no longer big enough? This is where realloc comes to the rescue. It resizes your existing memory block. Say your original block holds the numbers 10, 20, and 30. When we call realloc to double the size, it doesn't just hand us new empty space. It actually faithfully copies over our 10, 20, and 30 into the new block, and then leaves the extra space ready to be filled. If the new size is bigger, it grows and keeps the data. If it's smaller, it shrinks but still keeps the first part of your data. It just dynamically adjusts to whatever your project needs. But hey, I need to slow down for a second here, because dealing with memory dynamically introduces a literally massive risk: a memory leak. This right here is the silent killer of C programs. It happens when you fail to release memory you no longer need. And over time, your program just eats up more and more RAM until it completely crashes. And careless resizing is a prime suspect for causing them. Let's see how that ties into a really critical safety lesson. Think about the dangerous way to resize memory. if you try to expand your memory by assigning realloc directly back to your original pointer variable, and that reallocation fails, the function returns null. You've just completely overwritten your only key to the original data. It's gone. Poof. Leaking memory into the ether. The bulletproof way: always use a temporary pointer. You call realloc and assign it to a temp pointer. Then you check if that temp pointer is null. If it failed, your original pointer is perfectly safe. You only update your main pointer if the resizing was 100% successful. Moving right along, Section 4, Pro Coding Habits, Safety Equipment. In a physical workshop, you wear safety goggles and gloves. In C, your safety equipment consists of 3 absolute must-have habits. Tip 1, code structure. Cramming everything onto one line makes it a nightmare to read. Use proper spacing and indentation. Make it readable. Tip 2, use meaningful names. Calling a variable X tells us absolutely nothing. Calling it student_grades tells us exactly what that memory is doing. And tip 3, which is honestly the most important habit, always check return values. Every single time you allocate memory, immediately check if that pointer is null. Never, ever skip this step. If the machine didn't give you the materials you asked for, your program needs to know before it tries to build something with them. Another absolutely crucial piece of safety equipment is the include guard. Think of this as your compiler's gatekeeper. As your project gets bigger, you're going to have multiple files including the exact same headers. If a header gets included twice, the compiler totally panics and throws a bunch of errors. The include guard uses @IfNotDefined, which just means if not defined, to check if the gate is already open. If it is, it skips the file. If not, it opens the gate, defines the file, and compiles it exactly once. It guarantees your blueprints are only read one single time. Almost there. Section 5, the memory detective, inspecting the final work. Every master craftsman brings in a really harsh building inspector to track down any invisible flaws before shipping a final product. Now, our inspector talks in a bit of a matrix, so let's quickly decode the detective's log. If you see the phrase "definitely lost," hit the alarms. You have a memory leak. You forgot to free something. If you see invalid read/write, you were trying to access memory you shouldn't, like stepping totally out of bounds. But if you see all heap blocks were freed, congratulations, your code is flawless. No leaks at all. And the name of this detective? Valgrind. It is an unbelievably powerful command line tool. Take a bad scenario where you malloc 100 bytes and then immediately exit the function without freeing it. If you run Valgrind on that, it literally shouts at you, "Definitely lost 100 bytes." It catches the leak red-handed. But if you do it right, you allocate, you remember to use the free function on your pointer, and then return, Valgrind comes back with, "All heap blocks were freed. Clean bill of health." Valgrind is completely non-negotiable for C developers. Okay, let's actually pause for a quick interactive check to see if we've got this down. I want you to really think about this. If you malloc 100 bytes of memory and assign it to a pointer, and then right on the very next line, you assign that exact same pointer to a brand new malloc of 200 bytes without using the free function in between, is that a memory leak? All right, let's see how you did. For the first one, remember that malloc doesn't actually give you 10 integers. It just gives you 10 bytes. So trying to access an index of 10 is wildly out of bounds. For the second one, calloc automatically zeroes everything out, so it safely prints 0. And for our big question, yes, no way around it. That is absolutely a memory leak. Because you overwrote the pointer variable without freeing it first, you lost the address to those original 100 bytes forever. You literally have no way to clean them up. Looking at all of this, there is one golden rule that stands out above the rest to really cement your new safety habits. Always check if malloc, calloc, or realloc returned null. If you don't check, you are just driving completely blind. And that brings us to our final master blueprint. This one-page summary is your ultimate cheat sheet. It brings together allocating, zeroing out, resizing, exiting with status codes, freeing the memory, and inspecting it all with Valgrind. Plus, it highlights our golden rules. Check for null, free what you allocate, and run Valgrind. Now, I have a somewhat provocative challenge to leave you with today. Think about the C code you're writing right now. If you ran Valgrind on it this very second, would it pass the test? Try it out and see what the detective actually finds. Thanks so much for joining me in the workshop today, and I'll see you next time.